This is lesson 6.3. We will be multiplying a vector by a scalar. So we've already talked about the quantities, the terms vector and scalar. A vector is a quantity that has both magnitude and direction. And a scalar is a quantity that has only a magnitude. So when we're doing this, we're going to find out, we're basically going to start with a vector, and a scalar multiplier just says take that vector and multiply it by 2. Let's say this vector represents the velocity of your car. You're heading, northeast at 10 kilometers per hour. What happens if you double that speed? What would that vector be? What happens if you double your velocity? Well, your new resultant vector would simply be twice as long as the original vector, okay? You could also think of, okay, what happens if I go half the velocity? Okay, your vector would simply be cut in half. So we're going to be given a vector. We're going to call it vector v. And the scalar is just going to be the value that this vector gets multiplied by. And the scalar is often represented by the letter k. Okay, so a scalar multiple of v is kv. Okay? Now in this case, you've taken vector v and you've multiplied it by k. So it's a multiple of v, just like 15 and 20 are multiples of 5. You take 5, you multiply it by 3, you get 15. You take it and multiply it by 4, you get 20. If you take v and you multiply it by k, you get k times v. Okay? So this vector, the vector kv, is absolute value of k, the magnitude of k. It is k times as long as vector v, and its magnitude then, so its magnitude, so magnitude, we're not worrying about direction, so they're both going to be absolute values. Its magnitude is the absolute value of k times the absolute value of the vector v. A couple other things to note. What can happen to the vector v when you multiply it by a scalar? Well, it's the same as any other integer. If you multiply it by a positive value, it will continue to be represented in the same direction. But if you multiply it by a scalar that has a negative value, if k is less than 0, then we'll be flipping this vector around. It will be heading in the opposite direction. So if k is greater than 0, then kv has the same direction as vector v. If k is less than 0, then kv has opposite direction to vector v. One last note, a vector, and its scalar multiple are parallel. A vector and its scalar multiple are parallel to one another, That makes perfect sense because in the situation where you have k, which is a scalar, and v, which is a vector, only the vector is going to determine the direction. A vector is a quantity with magnitude and direction. The scalar can only affect the magnitude of the vector. It cannot affect the direction. So if you take any vector and you multiply it by a scalar, it's going to be parallel to the original vector. All right, example 1, we are looking at a bunch of diagrams of vectors, and we're going to identify which of them is a scalar multiple of vector v, and then we're going to determine that scalar multiple of each. So first thing, Let's just make a list of the ones that are scalar multiples of v. We've said that the scalar multiple k can change the magnitude but not the direction. But k can be less than 0, which would give the vector the opposite direction. So we're looking for any vectors that are parallel to vector v. And we'll just go through vector A. He looks parallel. Vector B is not parallel to vector v, so it's not a scalar multiple. The direction has been changed. C is, D is, E is not, it's vertical, E, F is. Okay, so we have 4 that are scalar multiples of vector v, and now in order to determine what that scalar multiple is, we really need to be able to measure our vectors, because we're talking about a magnitude, a scalar multiple. It's going to change the magnitude. So here's vector v, it's 2 centimeters long. So if I look at vector A here, vector A is 6 centimeters long. That would give us a scalar multiple of 3. So for A, if I'm dealing with A, trace that across here, k equals 3, because vector A is 3 times the length of vector v. Vector C, use my ruler the right way here, is also 2 centimeters. So it has the same direction and the same length. So the scalar multiple there is 1. The scalar multiple is 1. That's because multiplying anything by 1 is not going to change its value. D is measuring 1 centimeter. That's half the length, but it's also going the opposite direction. So the scalar multiplier to transform vector v into vector d is going to be negative because it's a change of direction, and it is half the length, so half the magnitude. The last one here is vector f. It's also in the negative direction. It's opposite, and it is 4 centimeters long, which is twice as long, which gives us a scalar multiple of -2. Now we know that the other vectors are not scalar multiples of vector v because they are not parallel. Example 2, we are going to represent a scalar multiple of a vector. So we're given vector u. We are told its magnitude is 100 kilometers per hour. Its direction is 40 degrees east of north. And so I've just set up, I've got A, B, C, and I've set up 3 cardinal planes. And we're going to go from there. So all I have to do is draw an arrow that represents each new vector based on vector u. So I need 3u. So is the direction going to change? Nope. Multiplying by a scalar keeps the same direction. It doesn't change the direction. It only changes the magnitude. The magnitude is going to be multiplied by 3, which means its velocity, whatever is traveling here, the velocity is now 300 kilometers per hour. And I need to represent that by a vector that is 3 times as long as vector u. And vector u I have is 3, we're going to call that 3 centimeters, which means that my new vector will be 9 centimeters, and I need to make sure it's parallel. Thankfully my ruler is straight, and that kind of looks pretty good. So 9 centimeters up to the end. Okay, this is the vector 3u, and the velocity is 300 kilometers per hour. And I also want to indicate that we are at an angle of 40 degrees here. So the arrow is 3 times as long, and we're heading at a quadrant bearing of north, 40, east. All right, let's look at 0.5u. All that means is I'm going to take half the length of u going the same direction. So we've got a vector that is 1.5 centimeters long, 1.5 centimeters long, the vector 0.5u. It has a velocity of 50 kilometers per hour, and we're heading again same direction, 40 degrees north, 40 degrees east of north. And our last one, the magnitude is being doubled, but we're heading the opposite direction. So I'm going to head down here, and we're going, it was 3 centimeters, so we're looking at 2 centimeters, sorry, 6 centimeters, 2 times that. There's 6 centimeters. Okay, this is the vector -2u. And the velocity, if we were at 100, we've got now -200. So we're at -200 kilometers per hour. Now the angle is the only little tricky part on this one that you have to think about, because if I think about this, if I have my original vector kind of there as a dotted line and this was 40 degrees, okay, that tells me that this is going to be 40 degrees. It's an opposite angle, okay? And so we're looking at west of south, 40 degrees. So we've got south, 40 degrees west. That is the direction that we're heading with a velocity of negative 200 kilometers per hour. I guess we don't actually need, the velocity would be negative 200 kilometers an hour if our direction was still north 40 east, but we've changed the direction, which means we're just heading 200 kilometers an hour in this direction, so I don't actually need that negative 200 negative sign in front of it. I'm going 200 kilometers an hour in this new direction. This new direction explains the negative symbol here. Quick little note here on collinear vectors. So for example, well, we'll just talk about it. Vectors are collinear if they lie on a straight line when arranged tail to tail. So collinear vectors are vectors that lie on a straight line. Vectors that lie on a straight line when arranged tail to tail. So we're going to give ourselves two vectors here. We're going to give ourselves vector u and then tail to tail. So we're going to bring in here in purple, we're going to bring in vector v, and it is going to be collinear with vector u. Okay, so they're collinear, they lie on the same line, they're arranged tail to tail, but they're parallel, they're going the same direction, so they lie right on top of each other. That in this case, these are always going to be multiples of each other. You could always take u and multiply it by a scalar multiplier, scalar factor, in order to get v, and same to get from v to u. They're also heading the same direction, okay? In this case, at any rate. A couple other notes that we want to say that are true about non-zero vectors, u and v. U and v are scalar multiples of each other. U and v are scalar multiples of each other. That means that u can be equated to k times vector v, and vice versa. V equals k times u, but the k would be different. The scalar multiple would be different. What else do we have? We have u and v are collinear and parallel. Okay, this will be true about non-zero vectors. And all of these statements actually are the same. They say the same thing, okay? They say the same thing. That means this is, if this is true, then this is true. If this is true, then this is true. If this is true, then that's true. If this is true, then that's true, if that makes sense. Okay, so all of these things are true if one of them is true about the relationship between u and v. This is our last note before our final example for the lesson, and there are no real surprises here. The rules of algebra that we've used when working with variables, when working with integers, the same rules apply to working with vectors. So a couple of the properties that we want to make sure we are familiar with and bringing to mind are the distributive property. Distributive property. These are things we can use when we're solving problems with vectors. The distributive property says that if we have some scalar multiplier and we have a group of two vectors, u and v, then that is equal to k times the vector u plus k times the vector v. Again, that should be no surprise. This is distribution, often symbolized by a little arrow there. The k gets multiplied by the u, and the k gets multiplied by the v, and you add them up. Another one is the associative property. Associative property. This is another one that we really do without thinking. There's nothing too challenging about it, but let's say we have scalars a and b, and they're being multiplied together, and then it's being multiplied by vector v. Well, if it's more convenient, you can rearrange this, right? There's just in between a and b is multiplication, in between this group and that is multiplication. It's multiplication all around here. So if it's more convenient, you can actually multiply vector v by the scalar b first, then multiply by the scalar a. And the last one is the identity property. Again, another one that you just do automatically. That is, for any vector v, if we take a scalar multiple of 1, and we go 1 times v, well, that's just equal to v. Anything times itself, anything times 1 is just itself. All right, let's head into example 3. Okay, we have trapezoid ABCD, and we are told that BC is parallel to AD, so vector V is parallel to line segment AD. We are also told that AD is 3 times BC. So AD has a scalar multiple of, it's 3 times the vector V there. What else do we know? We are going to let the vector AB be called U and the vector BC be called V. I don't need to write that. And we're going to express AD, BD, and CD as linear combinations of vector U and vector V. So we're going to express AD, BD, and CD as linear combinations of U and V. Well, we'll start easy. We'll start with the line segment AD, because we already know that AD is 3 times BC, so it's 3 times the length of BC, and we are told that BC is the same as vector V. So we're going to go ahead and express AD as 3 times the vector V. All right, let's look at BD. How do we create BD? Well, BD is BA plus AD. Okay, we already have an expression for AD, and BA is the opposite of AB, which is vector U. Okay, so let's just go back to where we were. We're going from B to D. We're going to go BA plus AD. That will get us there. But we need to express it in terms of U and V. Well, BA is the opposite of vector U. So that's negative U. And AD we already determined was 3 times vector V. So we're going to add 3V. And that is done. All right, let's look at CD. CD. Well, how do we get from C to D using these vectors? Okay, we're actually going to work our way around the trapezoid backwards. We're going to go, because we have an expression for CB, we have an expression for BA, and we have an expression for AD. Okay, so CB plus BA plus AD, that will work us in order from tail to head all the way around the trapezoid. And now representing those as scalar multiples of u and v, linear combinations of u and v, we have CB, that's the opposite of v, so we have negative v. BA is the opposite of u, so we have minus u, or you could write this as plus negative u. And then we have AD, which is 3 times vector v, so we're going to add 3v. And now we can use commutative property of addition or subtraction, and we can just kind of combine like terms, basically. We have negative u, we have a negative v and positive 3v, that's going to leave us with plus 2v. All right, that's commutative property and associative property at work. Your practice problems can be found on page 334. You would be responsible for being able to do numbers 1 through 19. Enjoy.